Oh, okay.
I started, yeah.
Oh, okay, great. All right, well, welcome to the second day of the time resolved X-ray opportunities workshop. Xiaoyi will be hosting mostly. I'm just doing a short introduction here. I've got a few slides and I will try to remember how to do that. I've got to switch things, don't I? How does this look?
Yeah,
Okay.
so
All right, so just to get us started, the APS, as you know, has been turned off and the upgrade construction is underway. And it was a little disconcerting to come in the other day and see nothing in our first optical enclosure, but this is the 7IDA hutch, and it's not quite nothing. There's still the first table here with mask and stuff like that, but that's all coming out later. And but that's where we are, and everything that was in here has been moved into the B hutch, and hopefully it will find some new home or get recycled somehow. There were a few questions about our new diffractometer setup for the 7ID hutch. So this is hide-on slide from yesterday. You see our nano diffraction instrument here, and we've actually got two separate detector holders. One is on the robot here, which is currently floating, but this will get connected in due time. So we'll be able to have a detector at a short distance from the sample, a relatively short distance, like about a meter, and that will be able to cover a large angular range. We've also got this far field detector positioner on this arc here, and that'll be about 3 meters from the source, from the sample, sorry. And that'll be more optimized for coherence. So just to show a little bit more here, in this picture, we don't have the sample stages or the KB mirrors here, but they would go over here. The detector can move on an arc from basically 0 up to 60 degrees in 2 theta, and it can also go up a little bit, so sort of like mostly horizontal scattering. And the detector, actually this arrow is a little bit off. The detector would go right up here. This is at the highest position of it. And again, the robot's not shown here. And this is also probably less relevant to most of you if this is the spectroscopy people who are showing up today. But this is one of the enhancements that for Sector 7. And again, the workshop agenda, we're on the right side here. Xiaoyi Zhang will chair it, and I will stop sharing.
okay.
And turn it over to her.
Okay, I don't have slides. So thank you, Don, and thank you all for attending the second day of our workshop. So the talk today focuses on time-resolved X-ray spectroscopy. So like yesterday, again, today we have a set of wonderful speakers. So we have a total of 5 exciting talks today, and with 4 given by external speakers and 1 by a beamline staff. So each external speakers has been allocated 30 minutes. So we kindly ask to keep the talk around like 25-26 minutes to allow enough time for questions. And I will give a 4-minute warning. And our first speaker today is Lin Chen, who is an Argonne Distinguished Fellow and a professor of chemistry in Northwestern University. Ning is the one who did the first pump probe X-ray absorbing spectroscopy experiment at APS more than 20 years ago. So, the title of her talk today is Excited State Trajectories in Photoactive Transition Metal Complexes Probed by Ultrafast Laser X-ray Spectroscopies and Scattering. So, welcome, Ning.
You're muted, Lynn.
Sorry, I'm mute. Okay. Yeah, thank you so much. And this is I'm trying to. Okay, can you hear the screen? Can you see the screen properly?
Yes.
Okay. Yeah, thank you so much for the introduction. And of course, I'm very excited about the next phase of the APS and looking forward to do a lot more experiment here. As Xiaoyi said, I started at 11 IDD almost from day one. Actually is from day one, was from day one. So it has been a long time. So I would just go through some the journeys with you. Some of you already heard something, but first I'd like to thank my colleagues in the solar energy conversion group at Argonne, and also my group in you can see my cursor. Should I change it to the?
Yeah, we can see your cursor.
Okay, so this is the group in Northwestern, as well as the team, a team of collaborators. When we went to the LCLS did experiment. So that's the so particularly the laser experiment was done by Pyeong-sang Kim mainly, and the other I will shout out during the talk. Okay, so our topics mainly focus on solar energy conversion and light generate the field and the electricity. There's a whole suite of photochemical process as expressed here. I'm not going to go through in the detail. And of course, this different phenomena span the multiple time scales as well as multiple spatial scales. And there are different light sources, including the laser synchrotron, tabletop, XUV, VUV, and X-felt to study all this. This is the collage of the different systems we have studied, including molecular species interfacial system and solid film, and here the hematite, and also electron transfer multiple donor receptor systems. So I'd like to give some example. This, you have seen this before probably. Yeah, that's the copper system we have studied since the beginning of the century, you can say. Yeah, so we did extensive photophysical studies using both laser and the X-ray, and that sort out the different lifetime and different structural change based, and I'm going to mention that later. And that evolved into using the copper complex as the light sensitizer dye, as those ruthenium dye molecules in the dye sensitized solar cell model system, injecting electron into TiO2, and then develop into the multiple metallic system doing the photo-induced electron transfer from one metal to the other. So fundamentally, the copper complex is very interesting with a lot of really significant signatures in the Zanes region and as well as the XF region. So I'm going to talk about focusing on the pre-etch in this slide. Basically, there is an argument about whether the copper excited state undergoes Young-Taylor distortion and ligate with the solvent molecule. So that's the so-called exaplex model. And this has been long debate in the community. And I think we have the answer now. It is the one, it's well shielded like this one, and then this excited state and the ground state chemically generated copper 2 has this pre-etch due to the depletion of the D electron. But in the last shielded one, the ground state, the copper-2 does not have that because the ligation pushed that 1s2 3d to higher energy. And more recent study with Gregory Smolentsov, he actually could calculate this particular feature as a function of the distance between the ligand and the solvent and the copper center in the excited state. So that solved the mystery. Basically, the excited state does interact with the solvent, but the solvent, this indicative, the solvent peak, if you have a ligated solvent, you're going to push this peak to the higher energy. Then we move on. This is many years later, we actually did the X-ray scattering at the LCLS with this iodine substituted at the 2,9 position. So iodine has very heavy, the high scattering cross section. So we were able to obtain the two modes. One is the motion between the two half. Oops, sorry. I'm trying to make the movie going. So the motion between the two half. The other is the flattening angle. As there's a flattening angle, there's the oscillation of the two half, basically copper to nitrogen distance. And then when we projected X-ray scattering trajectory onto the calculated potential energy surface, as well as calculating the spin orbit coupling on each point, on different points of this excited state and potential energy surface, we found out that, first of all, two very interesting things happening is the molecule has its own choreography, because when is the copper nitrogen distance it's long, then it can flatten the angle. But when it's compressed, the angle cannot flatten, it remains the same. So the next cycle, when it's extended again, the copper nitrogen distance, it can flatten further. And also the spin orbit coupling that determines the intersystem crossing only matters with the angle, but now the distance. And so we further study this interfacial charge transfer. That's G.R. Huang. And this is actually obtained as 97% of a quantum yield of an initial injection from the singlet state. So that compete with the triplet state. That's also obtained from this the 11 IDD. And that was further proved by the study done by Michael Mara and others, and actually looking at the electron injection using the characteristic peak at the copper K edge, looking at the oxidation change of the copper, because copper 1 to copper 2, this peak actually reduced due to the various structural change, both electronic and nuclear structural change. And Michael and others did the work that looking at the depletion kinetics of this feature. So in the solution, using taking advantage of this program Diagenin developed at 11 IDD, take the snapshot of all the consecutive X-ray pulses, and we were able to detect the kinetics in solution. It matches the optical study in the solution about 150 nanosecond. However, when it's connected to the bind to the TiO2, notice there's two different time scales. So this is up to the microsecond, still flat. So that's the injection into the TiO2, and that's a sustainable at least about the 30–40%, but the remaining actually probably recombine at the surface. So this study actually inspired us to examine the electron transfer directions. So that's currently Karen Mulford in the CSE is designing different molecules. So basically, that's if the electron transfers going in the same direction as the electron injection, and that's we're hoping to improve this sustainable electron injection rate and sustain the longer charge separation. Now, and that copper work is expanded to the dimetallic complex. In this particular case is the ruthenium and the copper. That was done when Dugan was a postdoc at Argonne. So he was able to sort out at the copper KH and the ruthenium KH, and there are two different depletion time constants. One is the instantaneous, the other one is about the 60 picosecond. While in the ruthenium KH, ruthenium is supposed to have much longer excited lifetime, but due to the intermetal charge transfer, the ruthenium KH signals quickly depleted. So this is related to one in the artificial photosynthesis, one try to design the system, have a directional, unidirectional electron transfer, and thus can have the similar to the Z scheme in the natural photosynthesis, have a reduction and oxidation at different ends. So Dugan analyzed this combined with both XTA as well as optical studies, and he was able to find out the mechanism of this photo-induced the process, basically because the ruthenium block and the copper block optically they absorb the visible photon in the same region. So one cannot just excite one, not the other. So Dugan was able to sort out that if the ruthenium get excited and this charge transfer going to go through the ligand, then the bridge, then at that moment, the copper going to donate electron or to ruthenium, and then finally the copper recover by the fourth step. But if copper get excited, it's going 1, 2, but there's no intermetallic charge transfer, and then this charge going to recover. So that also rationalized by the optical TA as well as the energetics of the different redox and excited states. I'm not going to into the detail. And then we also studied this platinum-platinum dimer complex. And in this complex, the two platinum in the 5DZ square create the binding sigma bound, binding and anti-binding electrons, and photo excitation deplete anti-binding electrons, and there's the bound order going to be increased in the excited state. So our collaborator, Phil Caslano group, was able to synthesize a different ligand and then modulate the orbital energy, and that caused the consequence in the excited trajectories. And we first did the broadband pump probe optical experiment. So this showing this the absorption and emission of these 4 different complexes. I think the strength is we have a whole sequence, 4 of them, so we were able to sort out the different factors affecting excited state trajectory. So the very first experiment was done at APS. That was when Jenny Lockhart was the director's fellow at Argonne. So she was able to extract the bound distance shortening in the MMLCT triplet state, and also following this excited state, using taking advantage again the consecutive X-ray pulses and follow this. And then that work was followed up by Nick Weingart as my student and published another paper recently. Now, we also did the scattering at the 11 IDD, but I'm going to skip that. So jump into the experiment we done in the LCLS. So obviously, there's no need here to introduce this basic of X-ray solution scattering, but I just tell you the result. This basic, the raw data, and we were able to plot one Q, larger Q and smaller Q. So as you can see, there's a first there's oscillatory signals, and then the signal response time are different. And Dennis Lashev was able to analyze the data, extract the frequency of the oscillation, but then he discovered this asymmetry of this, although it's not very obvious, but he was able to extract this two different frequencies. And this one has been just recently published in the Angawanti Chemie. The main point is that Dennis and others was able to extract the two coordinates. One is the PT-PT distance, the other one is the ligand angle. And obviously the ligand angle signal is noisy and we cannot really see the oscillation, but from this oscillation and project onto this the excited state potential energy contour, and it was able to extract this so-called spin vibronic mechanism for intersystem crossing. Again, there's no time for the detail. And Pyeong-Sang Kim, using the optical studies and using the really short laser pulses with a 20 femtosecond pulse, using the broadband TA, and looking at the vibration wave packet motion. So what this is, let's see, I can get this going. Yeah, okay, sorry, I think it's going too fast. Basically, the vibrational wave packet motion in excited state that can be captured by the coherent vibrational wave packet. So that's a blue and the red give you the different polarity of the oscillation, and this dashed line give you the node of the potential energy surface. Again, he was able to sort out the different kinetics of using the excited vibrational wave packet motion, and the rationalize is as if this Frank Condon state with the same geometry as the ground state is close to conical intersection of a vibrational of the triplet state, it undergoes really fast in intersystem crossing, much faster than the period of the PT-PT stretching frequency. That's the coherence maintained. And also that could have two different parallel pathways. That's in this case, one is far away, only one pathway is sustainable, but this is close, both pathway can be available. So that's why we can use this actually sort out the excited state pathway. And Shanawat, my postdoc in Northwestern, actually further this study using 2DES, the two-dimensional electronic spectroscopy. Again, I'm not going to go into the detail. The main point that he was able to sort out the time sequence of the vibrational wave packet motion and find positive evidence about this intermediate triplet state across the different complexes. And this work actually just being accepted by nature. The main point is that the APS study enable us to look further, but then we also push forward to the faster time scale. And this whole picture is that we can looking at spin orbit coupling, and that determines the intersystem crossing rate. But we cannot just looking at the first term in the wave function overlaps through the spin orbit coupling Hamiltonian. there's also the other structural factor need to be included. In particular, in this case, when the incandescent state is close to conical intersection, the vibrational motion enable the crossing of this two state, and that's actually break the Born-Oppenheimer approximation limit. And in that case, the vibrational motion at this point become a vectorial instead of oscillation around the equilibrium position. So basically, that's what we learned, but we start from the APS. And then we move on the other topic, which is the electronic nuclear structures of this model complex for oxygen evolving reaction catalyst, OER reaction. So this is based on the cobalt oxide and co-PI. I'm going to mention that even later. So Ryan Haight actually did the study with Dugan, and then both are postdoc at Argonne, and able to use both the X-ray absorption and RIX, and as well as the soft X-ray at the ALS to look at this particular complex and sort out both the electronic coupling, the electron hopping across the cobalt, as well as the evidence of this the structure of the cobalt-4 chemically generated cobalt-4. Then Emily Spranger-Klein, and she continued, she mostly focused on this co-PI, which is extended structure that Dave Tiede and his postdoc also did the PDF studies on this. And what the main discovery she observed using also the X-ray spectroscopy is that if you excited in the blue light in this region, actually create the LMCT transition, so that the metal actually being reduced. But if you excite in the red region, and that is going to be oxidized. So in the previously, we always thought this is a electrochemical electrocatalyst. So the photo activity has not been examined. So Emily did that. Now, okay, so this continues that also looking into the wish list for the upgrade, and Justin Hoffman, now postdoc at Argonne, and we'll continue Emily's work looking at the co-PI, but under the in situ operando condition. So Justin designed the cell and in collaboration with Xiaoyi's team, and looking at this the photo activity. And so at that time they used the 400 nanometer excitation. So that's supposed to reduce the cobalt. That's what it is seen here. That's a preliminary result. But this indicative, this combination of the electrochemistry and the photochemistry could be could fit the need of a many catalysts that can have a photo activity in the future study. And the other thing is the multi-modal data collection. I know it's probably asking for too much, but I think it is possible. We have the Pilatus, we have the detector, the XES, XTA, and the scattering detector. And sometimes we need to have a multiple spatial scale structural information in the time domain. And the other two wish list, obviously, I understood that the APS upgrade going to have a much smaller beam profile. So then is it possible to utilize some previously applied the scheme for time resolved study? That's meaning the offset, the laser excitation and the X-ray probe. and to gain the time resolution due to the flow rate across these 2 points. Is it possible? So maybe that could be something enhanced data collection throughput. And the other one is many systems that you could have a multiple chromophores. So therefore, it would be also interesting. So ignore this squiggles here, just looking at the pulse sequence could have multiple laser pulse and excite the multiple chromophores for the study, and looking at the interference. And this, of course, may be one order magnitude more difficult, but nevertheless, I think it won't stop us from thinking of that. And then the last one, I think it's the last one, it has been in my mind is to generate optical transient grading and using the X-ray to probe the diffusion phenomena. The diffusion can be the charge population, and it can be a pressure gating or even thermal grading. So this is the very preliminary, but it has been in my mind for some while. So I think I'm going to stop here. And this is the summary of what our current approach, basically trying to link the structural energetic coherent dynamics with the directional electron transfer, charge accumulation, and catalysis. And I would really, really thank you for the staff member at the APS since day one. Yeah, so I'm very grateful for all these people and I have worked with. Thank you. I'll stop here.
Oh, thank you, Ning, for this really, really wonderful talk. And yeah, also thank you for the great wish list. Some of the items are actually also our wish list, like the multi-pump X-ray probe. Yeah, we are really serious.
Can I stop share, Xiaoyi?
I know, I think you also, yeah, there's also question time. No, yeah, you still need to share.
Okay, then
okay,
let's see
so,
what the question is that I
okay,
can bring
yeah,
up.
so any questions for Ning? We have time for several questions. I actually have a question on this first example, the copper one. It is very like surprise to me. The electron injection rate is only dependent on the angle, not the bond length. Often angles and bond lengths are coupled with each other. So it's difficult to disentangle the effect. Also, is there some fundamental reason like behind this, why the angle matters, not the bond length?
Okay, so yeah, that is it's a brand new result. It's unpublished. Oops, sorry. Yeah, that's unpublished. We are still sorting out, but maybe this could also I mean, this is just it is what it is right now. But we need to further to explain this. But what strikes me is the vibrational motion, actually, they are in phase with two different kinds of the motion actually in phase. And obviously, if you look across this, and these dot size are the same, right? These dots are same, but from here to here, it becomes smaller, smaller. So that fits the previous result that yeah, so basically this the quantum mechanical calculation based on the geometry. So that also means the geometry is really, really important.
Okay, thank you. Okay, I have question from Hao. So he have question about the cobalt PI. So he asked what is it, and it is used in the for this electrochemistry.
Oh, okay, okay.
Example. So he asked what is cobalt PI?
Yeah, okay, sorry. I'm trying to go too fast. I think it is the it is the so Nocera and the co-workers in 2008, they published a science paper on this co-PI. Basically, P meaning the phosphorus. So they proposed the phosphorus at the edge of this cobalt oxide. And my colleague Dave Tiede and others did a PDF, and that's actually indicate that there are about 13 cobalt atoms, and they still continue their work at the used to be 11 IDC, right? IDB, right? So, but now that's a I think that's still there, but
Yes.
maybe upgraded. So that's the catalyst, and there's a proposed model at the time was that this electro catalyst. So when you apply the external bias, that can oxidize to generate from cobalt 3 to cobalt 4, and this adjacent cobalt 4 would be the active center for the water oxidation. So water binds that and generate oxygen. So that is so if you search co-PI, you get a tons of the literature.
Okay, I think the follow-up is like how this is used in photochemistry.
That's again, it's the very new. That's why this is based on previously it's all electro catalyst. Right now we're doing both electro and the photo catalyst because it does absorb some photon, but even the absorbance is relatively low. However, we discovered a different light response in the UV. It's mostly LMCT transition in nature. So the electron density shifted from oxygen to cobalt, and but at the red light is going to create a oxidative a reaction and increase the oxidation state of cobalt. So it's brand new. So as you can see, the current going to the different direction. This is exciting in the red, it actually being oxidized. Excite in blue, going to reduce. Actually, Dugan did hematite when he was a postdoc, and I assumed the hematite could have a similar behavior. Maybe Dugan can comment on that.
Okay,
Thanks.
Thank you, Lin. So I think we are going to move to the next speaker. So up next is Professor Dugan Hayes from the Chemistry Department of Rhode Island University. The title of his talk is Mechanistic Investigation of Photochemistry of Photophysics at Transition Metals and Post-Transition Metals. It's all yours, Dugan.
All right, thanks so much. Can everyone hear me?
Yeah.
Okay, let me try to get my laser pointer. Okay, great. Yeah, thanks Xiaoyi. Thanks Don for putting together this really fantastic workshop. I learned a lot yesterday. It's really great to interact with the time-resolved X-ray community. That's not just the X-ray spectroscopy community that I am more familiar with. So I learned a lot yesterday. I'm excited to see what else people have to present today. I'm going to talk about, I'm going to do kind of a quick summary of two projects in my group where we are combining optical and X-ray transient absorption spectroscopy to look at photochemistry and photophysics at transition metals, and then talk a little bit about our work in doing time-resolved nuclear resonance spectroscopy and some ideas for the future. So the first part, I'm going to talk about what we were able to learn about copper-1 catalyzed 2+2 photocycle addition reactions. I'm going to go through this a little quickly because I've presented it at this point too many times, I think. But yeah, we're interested in this reaction because 2+2 photocycle additions give these very, very strange cyclobutane groups that are fairly challenging to synthesize conventionally, but are very, very common motifs in natural products and pharmaceuticals. And so photochemistry provides a straightforward single-step route to these cyclobutanes and has been used in a lot of classic syntheses in the past. We're interested in the copper catalyzed analog because while the mechanism of direct excitation or triplet sensitized photocyclodistion has been long established, the mechanism for the copper catalyzed version wasn't. And there have been many proposed mechanisms in the past invoking ligand to metal charge transfer states, metal to ligand charge transfer states, mechanisms where the copper is simply serving as a template, various intermediates. And so we thought at the very least we could answer the question of what the initial oxidation state of the copper is following photoexcitation. And so this was work led by my student Getmi Jayasekara, who's actually going to be starting a postdoc at Argonne with Karen Mulford very shortly. So I'm excited for that, but this is a measurement that we did at 11 IDD in 2019. So looking at the copper catalyzed dimerization of norbornene, and we get different spectra that look like this at 100 picoseconds, something pretty indescript at 150 nanoseconds, but then starting to resolve more features at long time scales. And at long time scales, we see that this feature is very reminiscent of a different spectrum corresponding to a lowering of coordination number for copper-1 species. So these are steady state different spectra published by Ed Solomon's group in the 80s. So what we were able to see when we added norbornene is this clear formation of a pre-edge feature at 100 picoseconds and an edge shift. These are, the hallmarks of oxidation of copper-1 to copper-2, like Lynn mentioned at the beginning of her talk. But by 150 nanoseconds, all those transient features are basically gone, suggesting that we're back into a copper-1 state. But the spectrum does continue to evolve primarily through the increase in the intensity of these 1s-4p features. And so comparing what we see at different time scales, at early and late time scales, we think we're seeing the triplet MLCT state at 100 picoseconds and lower coordinated, so an unbound copper-1 corresponding to product formation on a microsecond time scale. And this is just highlighting that we don't see those same features in copper without the norbornene. And so we're able to put together this Jablonski diagram showing the reaction trajectory that we were able to figure out so far, going through the singlet MLCT state to the triplet. And then what we think is happening is before the next X-ray pulse arrives, we're back into a triplet, or we're back into a copper-1 state, but it's still evolving. So we think that this is essentially an indirect sensitization of the ligand triplet state that we wouldn't be able to excite directly using 267 nanometers. So we did some time resolved, some kinetic traces at different energies in the X-ray transient absorption, and then followed this up with optical transient absorption as well. And then we were able to follow larger parts of the spectrum over long time scales by looking at all of the sequential X-ray pump pulses or probe pulses that arrived after the laser pump to get these slower kinetics. And by combining all of that with our optical transient absorption data, we were able to finally end up with this mechanism for the dimerization of norbornene. So we're able to find that we're in this triplet MLCT state within about 4.2 picoseconds. 18 nanoseconds is the time scale for that reverse electron transfer to give the triplet ligand centered state. And then the product forms on the time scale of a few microseconds. We also looked at cyclohexene, which differs from norbornene only in lacking that bridging methylene group. And we did see example or evidence for an increase in the ligand copper binding, but we didn't see any evidence of charge transfer, and we didn't see any optical transient absorption whatsoever. And so even though this isn't, direct evidence, and so we're talking about not seeing particular signals that we saw with norbornene, we still see this transient signal at long times corresponding to a lowering of coordination. And so we think this is consistent with mechanism where we first do a photoisomerization of cyclohexene to transcyclohexene that rebinds to the copper to react to give the final product. And so we see that norbornene and cyclohexene actually react through very, very different pathways despite being extremely similar to each other. So this was work we did several years ago at the same time, actually piggybacking off of that same beam time. We did some measurements of the photochemistry and photophysics of ferrate 6, which I'm just going to call ferrate from now on for the sake of simplicity. And we were interested in this because we were approached by someone in environmental engineering at URI who's interested in using it as a non-toxic compound for water treatment, since it's very strongly oxidizing, since it's iron 6, but it decomposes just to iron 3 oxides, which are of course non-toxic. We're interested because it's has potentially interesting photophysics, and also it's a very rare example of such a hypervalent transition metal complex. It's the only known shelf-stable iron 6 compound, and so we were surprised to find that there was essentially no literature on its time-resolved dynamics, and so we set out to fix that. So what had been done in the past were these studies of the efficiency of intermolecular charge transfer following photoexcitation of ferrate in degrading these common pharmaceutical contaminants in drinking water supplies. But these are all, steady state measurements of this slow intermolecular redox chemistry. We wanted to look at the intramolecular charge transfer following UV excitation into this triplet LMCT from the ground state triplet state and see what happens after that. And skip this, other than to say that the optical absorption spectrum of ferrate actually matches the Tanabe-Sugano diagram very well, which makes it easy for us to analyze our signals and also be able to pump into these individual bands and watch the kinetics from there. So there's lots of challenges associated with it that probably explain why no one had done this in the past, but we went ahead and did it in that same beam time. This was work led by my student Callie Antolini, and this is what we were able to see at 11 IDD. We got these really terrible looking single pulse, single probe pulse X-ray transient absorption spectra at 100 picoseconds and 153 nanoseconds, but we could average a lot together on the microsecond time scale to get better signal to noise and see that the 150 nanosecond spectrum looked more or less identical. So we weren't seeing too much activity in terms of evolution after 150 nanoseconds. And so I presented this work at an APS-U workshop that Xiaoyi invited me to give a talk at back in October of 2019. And Anne-Marie was there at the time and said, I really think this experiment could benefit from the high repetition rate capabilities at Sector 7. And so I said, yeah, it sounds great. So we applied for beam time. We got allocated beam time, I think, or it was supposed to be sometime in the spring of 2020. Everyone knows what happened then. And so fast forward about 2.5 years, and we finally got to do the measurement in February of 2022, and we got these really beautiful looking X-ray transient absorption spectra here. And the thing that was initially puzzling to us when we did these measurements was that the spectrum that we saw following UV excitation is actually consistent with a transient iron 6 metal centered state, not the iron 5 that we expected to see following the ligand to metal charge transfer. And indeed, it looks very similar to what we see when we excite using visible light, exciting that metal centered state directly. But you can see there are some small differences. And by 150 nanoseconds following visible excitation, we see no signature at all in the difference, but we do see this dip following UV excitation. And so these transient features correspond to moving an electron from the E into the T2 orbitals. So we get increased absorption on the red side of the pre-edge, lower absorption on the blue side of the pre-edge following visible excitation, and same following UV for the iron 6. But then at long times, what we have is this dip just corresponding to reduction of the iron 6 to iron 5 from the oxygen 2p electron. So we could do some linear combination fitting to see how much iron 5 and iron 6 we have, and look at these kinetics. We get very simple mono exponential kinetics following visible excitation with a time scale of about 4 nanoseconds that we can also follow using nanosecond optical transient absorption. And so we can start to put together what we're seeing here on this diagram. And so basically what we're thinking is following UV excitation, we are in this LMCT state, and that can branch between intersystem crossing to the quintet or internal conversion to the metal-centered state. And then this is what we were seeing predominantly at 100 picoseconds. That relaxes by the arrival time of the next X-ray pulse, and so all we observe at that point is this quintet LMCT. And so we can start putting timescales to this, regardless of which visible absorption band we pump into. We don't see any difference in the kinetics. And so this intraband relaxation is very, very fast. We can also compare what we see following visible absorption and near infrared absorption directly into this triplet T2 manifold that's fairly well separated from these triplet T1s. And then we actually do see a difference where we get this instantaneous growth at when we pump at 800 nanometers with the slower component that we see when we pump in the visible. And so we're assigning that to the relaxation to this triplet T2. And so putting all this together now, we can complete the photophysical relaxation branch. We then, of course, have to complete the photochemical side where we're making this metastable iron 5 species following UV excitation. This is challenging because most of the initial triplet LMCT goes through internal conversion, but we're able to see some additional time components here and compare that to our long time data, and then follow this up with pretty exhaustive optical transient absorption in the nanosecond pumping across the visible absorption, and then through some more detailed analysis of our ultra-fast UV excitation, we're able to figure out the branching ratio between these two pathways. And I'd be happy to talk about that in more detail if people are interested. But basically what we see is 8 picoseconds for internal conversion to these triplet T1 metal-centered states versus 45 picoseconds for intersystem crossing to this quintet LMCT state, which gives us a branching ratio of about 85% into the metal-centered state and 15% into the quintet. And so we do have these additional time constants that we're not really sure about. We think these have to do with the subsequent photochemistry of this iron 5 species. It's known that the truly metastable iron 5 species is actually equivalent to abstracting a hydrogen atom from the solvent by the excited ferrate 6 to form the ferrate 5 with a hydroxyl ligand. And so we think that could be this 250 picosecond time constant that we're seeing. We've done some isotope substitution studies, but haven't really been able to confirm that. But we were able to pretty definitively, I think, figure out this side of what's going on in ferrate 6. So this was recently published in JACS, and I think half the people in this workshop are on this author list right here. Here are kind of like the main conclusions of what we found out, but we have continued to work on this a little bit. And last summer, in fact, my student Callie was at Argonne on the DOE SEGSR fellowship, and she was able to work with Anne-Marie and Gilles at Sector 7 to do the transient X-ray emission measurements. And that's what's shown here. So aside from the fact that, our transient K alpha signal is essentially 0, we don't see any difference here. And our transient signal in the K beta is very, very, very weak. This is exciting in its own right because it occurred to us much later that this is actually, to our knowledge, the first example of even a steady state X-ray emission characterization of an iron 6 compound. So we think that that's pretty exciting and pretty unique in its own regard. But right, we don't see any difference in the K alpha following either UV or visible excitation. In the K beta, however, we see evidence for a slight increase in the K beta mainline, and perhaps a bit of a bleaching on the blue side, which I don't really have a good explanation for. We need to try to see what we can do in terms of binning this data to improve what we can see here. And then we also have the valence to core data, which was very exciting for us as well. So this is kind of the status of that. I would like to revisit this in the future at some point to try to try to improve what we can see in the K beta and see if there is a difference between UV and visible excitation and the branching of those two different pathways that we might see at later delay times only following UV excitation. So with that, I'm going to shift gears into something a little more exotic, perhaps, talking about our efforts toward time-resolved nuclear forward scattering. So this dates back to the work I did on hematite that Lynn mentioned when I was a postdoc at Argonne. And we were troubled to find that nearly all of the optical and X-ray transient absorption signal that we could see from hematite corresponds to laser-induced heating. We were able to identify some signatures that were unique to the electronic excitation, but yeah, most of this seemed to be thermal. And this wasn't new. This has been known for many years, and many examples of different organic and inorganic compounds that optical transient absorption in the solid state is plagued by these thermal artifacts. And, you know, in X-ray transient absorption, it's even worse because, you know, we might like to think about a metal K edge as being nicely divisible into the pre-edge, the Zanes, and the XFs. But, you know, in reality, we all know that there's many other possible things that can be going on here. We don't really have a good way of modeling this in terms of understanding the core hole screening. We have Debye-Waller broadening that is going to be substantially affected by laser-induced heating. Then we could also have shifts in the spectrum just arising from a change in the lattice following lattice expansion when it's heated. And then, of course, this very drastic lifetime broadening that makes everything challenging. So, you know, there's potential ways of getting around this, doing temperature control experiments, maybe doing Herfty analysis. But we thought maybe we could try to do pump probe Mossbauer spectroscopy since nuclear forward scattering or other nuclear resonance spectroscopies are done at synchrotrons, have been done at synchrotrons over the last several decades at the APS, specifically at sectors 3 and 30, a little bit at sector 14. So just a quick overview for the case of iron, which is by far the most studied Mossbauer nucleus, iron 57, we're probing this 14.4 keV nuclear transition. And you typically do it with a cobalt 57 radioisotope source. You're able to get these 3 parameters, the isomer shift, the quadrupole splitting, and the magnetic hyperfine splitting. And you can correlate that to spin, oxidation state, ligand geometry, covalency, things like that, and learn about the chemical environment by doing a nuclear spectroscopy, not an electronic spectroscopy, although it's reporting back on the electronic environment. You have these very narrow line widths due to this long lifetime of this excited state. And typically the problem with this, or you know, one of the challenges is that, and the reason this has to be done in the solid state is because these line widths are much smaller than the recoil energy for such a high energy photon. So these have to be done in the solid state. But the primary temperature dependence that you see in Mossbauer spectroscopy comes through this Lamb-Mossbauer factor, which is basically saying what is the probability of a 0 phonon nuclear excitation. And this just comes from the mean square displacement of the absorbers. And so we get this familiar Debye-Waller term here to give us this Lamb-Mossbauer factor that tells us how much our spectrum gets attenuated as temperature increases. And so here's some data that we have for these tin halide perovskites at temperatures from 7 Kelvin up to 200 Kelvin. You can see the spectrum gets attenuated, and we can fit this to the Debye model back at a Debye temperature and figure out the recoil-free fraction or the Lamb-Mossbauer factor that way. But importantly, what I want to stress here is that the magnitude of the absorption changes, but the spectral shape does not change at all. There is some change in the spectral shape coming from the second order Doppler effect. And this is just coming from now the mean square velocity of the absorbers. And so you get this very small shift that's approximately linear in temperature on the order of about 0.001 millimeters per second, which is the energy unit for Mossbauer spectroscopy per Kelvin. So there is some shift, but it's typically very small. So we've done a lot of steady state radioisotope Mossbauer spectroscopy in our group, but we're interested in doing this at a synchrotron, one, because we can get time resolution by doing the same thing that we do in X-ray transient absorption, combining optical excitation synchronized with the storage ring, but also because it gives us access to a much broader range of Mossbauer active nuclei. So here's all the Mossbauer active nuclei on the periodic table. Here are the ones that feasibly could at some point be measured at a synchrotron, and here are the ones that have currently been measured at a synchrotron. One of the big problems with or challenges in this approach is the fact that we can have these high resolution monochrometers at a nuclear resonance beamline that get us 1 milli eV bandwidth, but that's still much broader than our nuclear resonance. And so our temporal response, if we're doing this in the time domain, is often swamped out by prompt electronic scattering or electric scattering. So there are frequency domain approaches around this. We thought we could combine a frequency domain approach with laser excitation to get all the benefits of transient X-ray spectroscopy, but hopefully be mostly insensitive to thermal artifacts. First, though, we wanted to try this in a simpler manifestation by doing it in the time domain. And so this is called nuclear forward scattering. Basically, you excite your sample and then you get this quantum beating signal. So you're essentially doing time correlated single photon counting of the nuclear fluorescence, and you get these quantum beats that you can Fourier transform to get your frequency domain signal. And so after many years of COVID-related delays, we were finally able to try this last December. So this is my student Callie, who was at Argonne for 6 months, working with Michael Hu, beamline scientist at Sector 30, and many other people to really make this happen. Sheila and Anne-Marie were gracious enough to spend a lot of time working to move the laser setup from Sector 7 over to Sector 30 and incorporate it and take care of all the synchronization. And so we could combine it with the tin nuclear resonance beamline here. And so here's what we get. This is our steady state spectrum of tin 2 oxide thin film. We get a laser on and laser off spectrum. We can measure it with a tin 4 reference, so we get this quantum beating that will get us back our isomer shift relative to that. And then importantly, we can change our laser excitation from half the repetition rate of the storage ring to 1/23 the repetition rate. And we want to do this so that we average out any bunch-to-bunch differences between orbits by phase shifting as we go through every optical excitation. And so what we get here now is a drop. If we integrate the total counts that we have for each of those X-ray probe pulses, we can get a measure of the total nuclear absorption. And so this drop that we see with the laser corresponds to that laser-induced heating that's attenuating the overall spectrum. And we can fit the recovery of that and see how much the temperature changed at 2 different time points from this data from 1994, where we can look at the Lamb-Mossbauer factor as a function of temperature. We can then correlate that to the second order Doppler shift for the same material and see that we get a very small change in isomer shift that we'd expect here. So now we can take our laser off with and without the reference, fit this using the Kana software to get the quadrupole splitting and isomer shift, and then do it again with laser on, and we can see that we do indeed see differences that are more that are statistically significant and greater than what we'd expect from thermal effects alone. So these are the different spectra. We don't really know exactly what to make of these yet. This is still very much a work in progress. I just wanted to show something a little bit different for this workshop. And the last thing I'll say is, we still want to think about how we can broaden or increase the number of Mossbauer active nuclei from this to something closer to this. And so I have this schematic planned, and I have no idea if we'll ever really be able to try this, but for doing optically resolved nuclear resonance spectroscopy in a pump probe arrangement, but not to get time resolution. So this would be an X-ray pump optical probe measurement, and this would allow you to do measurements of materials in the solid, but also liquid and even gas phase. So here's an example of how we could do it for cesium by taking advantage of that recoil energy to shift our optical transitions and look at the isomeric shift on those following nuclear excitation. So with that, I'd like to thank everyone in my group, especially Callie, who worked really hard to get the Mossbauer working, and the ferrate, Gethmini for working on the copper photocycle edition, and then of course everyone in the time resolve research, AMO, and inelastic X-ray scattering groups at Argonne. And I'd be happy to take any questions.
Yeah, thank you, Dugan, for another wonderful talk. So I already say Dong Zhou, so you can speak up.
Hi, very nice talk. So I do have a question regarding your last slide about you want to do Mossbauer experiments on liquid and gas. You said,
Yeah.
How can you do that? Because as far as I know, the Mossbauer effect is basically, I mean, doesn't exist for liquid and for gas. That's why people have to do it. Yeah. So, but what kind of quantity are you trying to get from this kind of measurement?
So the idea here is that the synchrotron beam has bandwidth far greater than both the nuclear the nuclear resonance, but then also the recoil energy associated with absorption for, let's say, in this case, gas phase cesium. And so that bandwidth is going to cover all of those possible nuclear transitions. And so it's going to substantially Doppler shift everything that absorbs through that recoil, but it's going to be uniformly Doppler shifted. And that means that our optical transitions now are shifted out of band, way out of band with the natural line width of those transitions. And so we could take, do essentially step scanned high resolution optical spectroscopy on the nuclear excited state of cesium-133. And by measuring these optical transitions, we can then correlate them back to get the isomeric shift, and then also from there figure out our nuclear transitions. So yeah,
So technically, do you use a high resolution model for this one, or will you just use a
no, and that's one of the good things about this, that it does require, in the examples I've shown here, I'm imagining this would be most useful for these nuclei that have very high transition energies. And so the good thing about this, though, is that you don't have to monochromatize at all because it's optically detected. You're not detecting any X-ray photons whatsoever. And so the best thing to do is just take, the as much flux as you can. So even like a pink beam, for example, would be okay. And to fully excite everything, and then you're just doing optical detection. So this would be this, the setup right here. You'd have to, move from beamline to beamline, but in theory, you could do this at any beamline that has sufficiently high flux at these high energies.
That's really cool. Thanks.
Thank you. Yeah, I'd be happy to talk more about the details with you offline at some point, because I would really like to do this, but I have a feeling it's probably never going to happen.
Sure. I will be also very interested in learning more about this. Yeah.
Okay, and thank you, Dugan. So I think we are going to move to the next speaker. Our next speaker is Anne-Marie Marsh. So she is a physicist from the Atomic, Molecular, and Optical Physics group at Argonne. So the title of her talk today is Tracking Chemical Reactivity Across Multiple Time Scales with X-ray Spectroscopy. Thank you.
Well, good morning, everyone. Do I have the correct?
Yes. No, you need to switch the view.
You need to play
Swap the
the
display. Yeah. Yeah, that's good.
That's better?
Yeah.
Great.
That's good.
Okay. So good morning, everyone. Xiaoyi says I'm a member of the AMO physics group. Here's a recent picture. Over the last 10 years or so, we have been working to develop high rep rate laser pump X-ray probe spectroscopy in the DHUTCH at sector 7. We have pump lasers that can match the megahertz rep rate of the X-rays, and this lets us use the X-rays in a rather efficient fashion, so we can incorporate flux demanding techniques. And so we have incorporated emission spectroscopies along with absorption spectroscopies and their hybrids And we've shown that we can do this, all these techniques shown here in pump probe fashion. But this workshop's about looking ahead. And so what we're thinking about is that chemistry, particularly in liquids where a lot of chemistry happens, it occurs over a very, very broad range of timescales. And in order to really fully understand chemical reactivity, it'd be really nice to be able to track this chemistry across this broad timescales. And so to give you a flavor of what I'm talking about here, I have as an example a manganese complex that we have been studying with researchers at the University of Kansas and University of Michigan. That is an analog of a rhenium complex that's a really great CO2 reduction catalyst. But if we want to get rid of rhenium and replace it with earth-abundant manganese, it would work great, except for the fact that it degrades under light exposure. And so we've been trying to understand what exactly happens to it after it absorbs light. And so here you can see you have chemistry happening on fast time scales where you have CO ligand loss, and then solvent coordination. We can catch this at the LCLS. But then you have other things happening, the recombination. Then you have electron transfer. You can lose a bromine. You have dimerization, and all sorts of subsequent biomolecular reactions that happen out to the millisecond time scale. So the dream here is be able to track all these processes using X-rays in one go. And APS-U is going to be great for this because we will have finer X-ray temporal combs. So 324 bunch mode will be X-rays at 11 nanosecond spacing, and 48 bunch mode will be 77 nanosecond spacing. And so we can use the X-ray pump probe technique to capture many time scales all at one go. And Eli Koenigstein and Xiaoyi have shown that we can do this in 324 bunch mode, and we can use fancy asynchronous pumping schemes to get many delays all at once, and we can get these beautiful 2D plots. So this is what the future holds, and we're really excited about this. Okay, but the main topic for my talk today is our adventures studying iron hexacyanide in water. And so this is a rather simple molecule. Here's a brief introduction. It is iron 2 bound to 6 cyanide ligands. It's known as ferrocyanide. It's often found with its redox partner, iron 3 CN6, ferricyanide. It's a small, highly charged anion. It has strong hydrogen bonding between the CNs and the water molecules in the solvent. It's highly stable. First glance, all those cyanides look like it's a terrible thing, but they don't come off. And actually, fun fact, this is actually approved as a food additive. It's an anti-caking agent. But anyway, it's a textbook pi back bonding complex. The bonds between the iron and the cyanides are highly covalent, and it's a highly symmetric octahedral complex. And its history goes way, way back. And so I just wanted to share with you a fun little history story here. There's this, you can get a 5-part description of what people have pieced together about this at this website, chemistryreviews.org. But in 1706, Prussian blue was accidentally discovered, and this changed the art world. Actually, you could argue more than just the art world. But here's the story. So there was a paint manufacturer in Berlin, Johann Deisbach. He was trying to make red paint. And so he had this cochineal, which are an extract of ground up insects to get the red. And then you mix it with some iron, some potash, some potassium salts, and you can get this stable reddish, what they call lake. It's a paint. Okay, so he was trying to do this. He had run out of potash. So he goes to grab another container in his colleague's lab. Turns out it was mislabeled potash, and it contained iron cyanide. And so when he mixed it all together, did his routine, he ended up with this brilliant, beautiful blue color. And this was the first modern synthetic pigment, and it was really important because before this, blue paint or blue pigment was super expensive, and not many people can get it. So here we have an example of this beautiful woodblock print that is very familiar, I'm sure, but this is an example of the use of Prussian blue. The chemistry behind this is actually not trivial, but here's where ferrocyanide shows up. So that potash was contaminated with potassium cyanide. The cyanide reacts with the iron and it made ferrocyanide. And then ferrocyanide goes on to react to create the mixed valence compound that we call Prussian blue. That's iron 3, iron 2 hexacyanide. And it turns out that Prussian blue is actually a rather complex structure. It has a polymeric form, and the way the reactivity conditions can influence the structure and the properties. So it's a very interesting chemistry. I'll just show you, we get to enjoy the beautiful blue, Prussian blue color, because when we run our ferrocyanide samples in our OTA setup, the ferrocyanide solution is light yellow, but we end up with our originally clear tubing changing into this lovely blue color. So we get to enjoy it. But here is I think something that would be incredibly cool, to be able to use X-rays to track the reactivity of ferrocyanide all the way through to the creation of Prussian blue under different environmental conditions, temperature, pressure, concentrations, pH, all that, to understand how you can really control the production of Prussian blue, to use it for various things. So this is what I think APS-U can give us. Okay, so people have been studying this forever. And so the literature goes on ferrocyanide photochemistry goes way back. The oldest paper I have is 1951, where they're trying to understand what happens to ferrocyanide when you expose it to UV light. So it's a very stable complex, except under UV light exposure, it can start to degrade. And so these studies go way back. This paper refers to papers investigating this in 1905. In 1971, Sharomenstein kind of established what the primary reaction channels are for ferrocyanide. And there are two dominant reaction channels. One is you excite to a charge transfer to solvent state and release an electron that becomes hydrated. This produces ferricyanide. So we call that photooxidation. And then in parallel to this, you can have the photoequation reaction. So here you excite a DD transition that leads to a triplet state and anti-bonding orbital population, so that the CN ligand comes off. And then it's replaced by a water from the solvent. And so that's the photoequation reaction. And so if we pump at wavelengths longer than 310 nanometers, we can study just the equation reaction. For those shorter, we can study both of them together. And so now you may be asking, this has been studied forever. Isn't this all figured out? Why are we still studying this with X-rays? Well, the thing about the system is that it has been studied forever and things have been figured out, but it continues to be investigated in all these interesting places. So, you know, it's interesting for being a small, highly charged ion, and the way it structures water around, the way that the solvation changes during the equation reaction. These are interesting things to investigate, but it's also relevant for environmental pollution. If you have cyanide coming off, hydrogen cyanide, this is not such a great thing to have in the environment. It's relevant for prebiotic chemistry of early Earth. It's relevant for redox flow batteries, thermal galvanic cells, aqueous solar cells. It's also, Prussian blue itself is a great sorbent for radionuclide recovery. And so people are really interested for that. And then of course, it's a great model system for understanding X-ray spectra content. So there's a lot still to understand. Its chemistry is complex enough to investigate. Now for us, we began our studies way back in 2013 as we just needed a molecule. We wanted to see, can we do pump probe valence to core? And the valence to core signal is teeny tiny, so that, and we had our Johann spectrometer. at megahertz rates, is this even possible to measure a transient signal? We needed a complex that was light sensitive, but that we can make in huge quantities because we're going to have to acquire for a really, really long time. Ferrocyanide fit the bill. And so this is how we started investigating. We did measure some first time resolved valence decor. We've come a long way since this. But the interesting part is that while doing these measurements, we also started measuring the absorption spectra. And this is how we kind of got hooked. So now I just want to, I've shown this before, so I'm just going to go through this fairly quickly. But here's how we've gotten hooked studying the interesting the sample with X-rays. So we measured the absorption spectrum at the iron K edge, and so that's the top here in the black is the ground state spectrum. Here we were just pumping at longer wavelengths so that we were studying just the equation reaction. We were just wondering, can we catch the photoequated product? The yield is extremely small. The optical absorption coefficient is very small. We're going to make just a teeny tiny bit of this. Can we even capture the absorption spectrum? And so our laser pump signal is you can't see a difference from the ground state plot in the top figure. So we look at the difference signal, and we do in fact see a very, very nice difference spectrum after pumping. And it's, I have 2 time delays there. We see it at 215 picoseconds. And then we see it hasn't changed at all out at 153 nanoseconds. And so we thought, oh, cool. This must be the signature of the equated product. And then what we did is we did something a little bit crazy, but while doing this measurement, we also incorporated an optical probe in order to measure the amount of equated product we were producing. And so by doing this, we could determine the excitation fraction precisely. So we found we were producing 1.3%. And with this, we could reconstruct the absorption spectrum for the equated product. And that's what you see in red. And so this was pretty cool. We also studied this at 266 nanometer excitation, where we have both reaction channels. And so here you expect to see contributions from the 2 products, the equated product, but also ferricyanide. And so here we have 50 picosecond delay, 2 nanosecond delay, and 30 nanosecond delay. And you can see that the shape of the difference spectrum is changing here, as opposed to the equated situation. And so we said, okay, well, can we reconstruct these different spectra using what we know for the shape of the ferricyanide spectrum, which we can measure statically, and what we just measured for the equated spectrum. So we can take these 2 pieces and reconstruct. And the answer is yes. And so here's our measured difference signal. Here's the ferricyanide component. Here's the subtraction of the measured signal minus ferricyanide component. So what I call the residual. And then in the green is the difference spectral that we measured for the equated product. And you can see it matches very well. And so from this, we can say, okay, at 50 picoseconds, we have 7% ferricyanide and about 2% equated product. And we can do this the same for the other 2 delays. You can see that the amount of ferricyanide decreases with time, and the amount of equated stays constant, except that at longer delay, it seems like it's increasing a bit. And so now here, I want you to use your eagle eyes and look in very closely at the difference between the green and the residual curves here. At 2 nanoseconds, they match quite well. At long delay, there are some slight discrepancies. There's something else there. And then at short delay, there are slight discrepancies. There's something else there. So now long delay, this is what Eli Königstein has been investigating what's happening here. It's looking like we're making more equated as the ferricyanide is decaying. And so he has applied his asynchronous multiprobe to try to understand what's happening there. What I'm going to tell you about now is our investigation on what was happening at the very shortest times, where we're pumping within the X-ray temporal profile. So here again on the top, this is the the different signal now pumping at longer wavelengths, so only the equated reaction is occurring. And there is a difference at short time, 55 picoseconds, and longer time, 215 picoseconds. Now, we were very careful to make sure that this was not some sort of nonlinear contribution, because this molecule likes to absorb multiphotons. So it's not. And so then we thought perhaps what we're seeing is a signature of a pentacoordinated intermediate. And so, long story short, we went ahead, we measured a whole bunch of Zanes at different delays, a whole bunch of kinetic scans at different energies, did principal component analysis, global fitting, and with all of that, we were able to, in fact, pull out the signature of the pentacoordinated species and reconstruct its spectrum. So that's what's shown in blue here. And so we could show that, so you absorb light, you create this pentacoordinated species, it decays with a time scale of 19 picoseconds, and then a water comes in to bind. Okay, so then we turn to our theory colleagues, collaborators, to say, does this make any sense? And so this is Neri Govind, Amity Anderson, and their postdoc, Daniel Nascimento, did some calculations for us. They did TD-DFT simulations of the pre-edge region. So the pre-edge region is particularly informative because it is the resonance is from 1s to 3D, and it can tell us about the geometry of the species, which helps us identify what we've got. And so their simulations are the solid lines. Our measurements are the black dots, and they agree beautifully. So I have different species involved here. The iron 3 we measured just statically by itself. Then there's ferrocyanide with one pre-edge peak. And then we have the pentacoordinated species, which can have two different geometries, a square pyramidal geometry and a trigonal bipyramidal geometry. And the pre-edge features here are very, very similar. We can't distinguish with our measurements, but overall it matches very well. And then the equated species matches very well. So this was pretty cool. And then Neri and Amity did some quantum mechanical, molecular dynamic simulations to try to understand what's happening here. So they start out with this first one here. They start out with the ferrocyanide in a triplet state, so that excited triplet state. And they find that it releases the CN, and it takes about 1.3 picoseconds for the CN to kind of fully make its way away from the complex. And this leaves it in this square pyramidal geometry. Then they looked at what happens to this triplet square pyramidal pentacoordinated species, and they found that it will fluctuate, but it's between the square pyramidal geometry and the trigonal bipyramidal geometry, and it will fluctuate between the two geometries on a time scale of about 3 to 4 picoseconds. Then they found if they, there's no simulation for this. Then if they bring a water in close, when the pentacoordinate is in a triplet state, it'll just spit it right back out. What needs to happen, the water needs to be close, and there needs to be a spin change for the water to stick. And so they showed that. So here's what's happening. They did some more analysis. The molecule spending, that pentacoordinated species is spending most of its time in the trigonal bipyramidal geometry, but then every 3 to 4 picoseconds, it has a small window of time where it's in a square pyramidal geometry, and this kind of opens it up to allow space for a water to approach. And so it's only those small snippets of time when equation can occur, and this kind of explains the long time scale. Okay, so this 3 to 4 picosecond time scale for this fluxional behavior, this implies a very small energy difference between these geometries. A rough estimate is a few kcal per mole. This is really small, and so this got us thinking this whole process must be really sensitive to the details of the solvent environment. And we were intrigued by this, and we wanted to investigate this. So we can't just spend all our time at the beamline consuming all the beam time. So we had to have an offline means of investigating this. So Chris Atolsky built an optical transient absorption setup in our 3rd floor lab based on our ferrous laser. And what we can do here is we can use the fact that the equated species has a distinct absorption at 450 nanometers, which is a region of the spectrum where the ground state does not absorb. So we can track this absorption feature as a function of time to see how this equation reaction occurs in different conditions. So different temperatures, counterions, different solvents, solvent mixtures, etc. And so here's just an example of some of Chris' data. We have, a 2D plot of delay versus time. To start, we're looking at the slower time scale in the picosecond region. And what you can see here is you see the blob. I should have gotten the laser pointer thing going. I don't actually know how to do that. Pointer options.
You can right click.
Pointer options.
Yeah, you can right
There
click.
we go.
first, Yeah.
You see this?
Yeah.
Awesome. Okay, so here is, this is time 0. And this feature here is our equated feature, and it grows in. And so we can take a slice here and just do a simple exponential fit, and we get a time constant. Here, it grows in at 25 point ±1 picosecond. So then now we're thinking, oh, okay, well, maybe we can measure rates versus temperature and see if this model makes sense, or Neary's model makes sense. So here we go. We think of transition state theory. Our starting species is the trigonal bipyramidal pentacoordinated species. Then the transition state is the square pyramidal. Final product is the equated. Okay, so Neary seems to think that this should be about a few kcal per mole. So here we go. We have our Arrhenius plot, and we have our measured rates as a function of temperature. We do a fit, and sure enough, we get about 3 kcal per mole. And so this is kind of cool. And we think that this is experimental evidence or support for the MD simulations. So this is kind of spiffy. Let's see here. How am I doing on time? Okay, I'm not terrible. Okay, so then we also thought, what else might this be sensitive to? And one thought we had is, do the counter ions matter? Now, why would I care about the counter ions? In Neary's simulations, he just kind of throws them in the box, in his simulation box, to neutralize the charge, but he pays no attention to where they are. However, a -4 charge is a high charge. And we found some papers in the literature do simulations that claim that the potassium counter ions are actually in the immediate vicinity of the anion. And then other papers, there's a study of terahertz that did terahertz spectroscopy that seems to imply that even at lower concentrations that we're operating at, we're at like 100 millimolar, ion pairing can be significant. And so our thought, it was like, well, if you've got this counter ion here, how does it possibly affect this equation reaction? So we investigated different counter ions: potassium, sodium, and rubidium, also cesium, but it's a little complicated. And we thank Dugan for synthesizing the rubidium and cesium for us. But so here, these are preliminary results, but what we see, okay, so to explain this, we did the 3 different temperatures, and then the top row are the absorption spectrum at 2.5 picoseconds. The bottom row is the absorption spectrum at 100 picoseconds. Here you can see the equated peak. And then the colors are: black is potassium ferrocyanide, the turquoise is sodium ferrocyanide, and pink is rubidium. What we see is the yields differ, goes in the order sodium, rubidium, and potassium. And there's also subtle differences in the spectral shape. And so we're still investigating this, but right now it looks like we might have, in some conditions, the pentacoordinated species still present at long time scales. So this is a little interesting. We're still working on this. Now, our thing is emission spectroscopy. Do we do emission spectroscopy? The answer is yes. I'm going to flash you the data, and I'm not going to talk about it unless you have questions, because I want to talk a little bit about some ahead for APS-U. But the idea here is that
Hey, Emily, sorry, you have 3 more minutes.
okay. So then I got to just jump through. The spin of the pentacoordinated is triplet, which is different from the ground state singlet. Emission is sensitive to this, and so we use our von Hamos spectrometer. We do see nice different signals that are consistent with the triplet state, but we also see a signal out a long time scale. We're still trying to parse this out. Okay, but so I wanted to just mention some ideas for some of the challenges that are ahead. There's lots of great opportunity, but there are a couple challenges. And one is being able, if we're going to track chemistry across these timescales, you end up with a mixture of stuff in your laser pump sample, and it's hard to separate the signals because you don't know how much of the stuff you have, and you don't necessarily know what the spectrum of the stuff is. So here, a multimodal approach can help. And so we have already demonstrated at 7, you can combine absorption, emission, and scattering together. We have also shown you can add optical transient absorption in with absorption spectroscopy. Having these 3 together gives you more information to be able to disentangle the different species. So this we think can be very valuable. And sector 25 is wonderful because we're going to have this ability to switch between monobeam and broad bandwidth beams. So you can actually do really good XES in the same time beam time as XAS, which is going to be great. Okay, the next challenge is that with APS-U, our X-rays get longer in time. So one idea here is to circumvent this and to maintain the time sensitivity that we presently have. We can incorporate time correlated single photon counting. So this is often applied to measure the fluorescence decay of optical fluorescence. But we're not going to be measuring the time decay of the X-ray fluorescence here. The idea is simply, this is a way of marking the X-ray absorption time relative to your pump pulse. And then you'll have to deconvolve the X-ray signal from the X-ray pulse shape, as we've already shown we can do, at least with APS now. But the IRFs for time correlated single photon counting can be small. I just show some values here. You can get down to 20 picoseconds. So this is kind of the level that we presently enjoy. Perhaps we can maintain it. So the last thing is that our 2D pixel array detectors are slow. So 48 bunch mode, I think we can gate them. 324 bunch mode, no. That's just not happening. So for our emissions studies that use our von Hamos spectrometer, shown here, we're using a Pilatus detector now. But really, here I show an image where we have many different spectra on lines here. We don't have to, this is just happens to be an image with many spectra. You don't have to have so many, but it's really just a line. It's all focused down to a line. So the idea is you use a 2D detector to align the spectrometer, but then move it out of the way and move in a line detector, which can be faster to then just measure the pump probe signal. So those are the ideas I have for ways to make sector 25 the best pump probe spectroscopy beamline there is. Just in conclusion, I think our dream is to track the chemical reactivity from beginning to end in different reaction conditions. APS-U and sector 25 is going to move us in this direction. I think there's lots of exciting new insights to come. So thank you for your attention.
Thank you for this wonderful talk. Also, again, thank you for all these suggestions. So yeah, I think some of them we already also think about it. So, and we have discussed the time at the end of this session. So I think for now, we only have time for one quick question. Okay, we can, yeah, do good, yeah.
But maybe this is more appropriate for the discussion time, but that teaser about the counter ion dependence, I'm sure that you expect me to ask about that. So what are you thinking in terms of how that might affect the rate? Because you're saying even at 110 picoseconds, you still think you see some evidence of the pentacoordinated?
Well, so this is tricky to understand so if you look the optical results, you have the equated feature, but then below we're catching the tail of another feature. And so Marco Reinhardt and Maja Sergi's group, he did his whole thesis on ferrocyanide, and he did a lot of studies. He assigns that tail we're catching to the pentacoordinated species. And our optical results show it is just not fully decayed, except at higher temperatures. So, but I don't know, this is all still preliminary, but my thought is that you just end up with this equilibrium where the equated species, there is perhaps a nearby triplet state that it can, convert to and then release the water that then it comes back on. There's some sort of equilibrium that exists there. And it might help us understand our emission data, which is really confusing us. But that's still very much a work in progress. But
okay, thanks.
Okay, thank you. And we are going to move to the next speaker. So up next is Dr. Dushie Mushera. So she is a group leader at the Instituto de Ciencia Materials de Madrid, Spain. I tried my best to say this. Okay, the title of her talk today is Unraveling the Mechanistic Pathways of Earth's Abundant Photosynthesizers and Solar Field Catalyst through Time-Resolved X-ray Spectroscopy. Welcome, Dushie. Oh, you are muted, I think. Oh. We cannot hear you. No. No, we still can't hear you. Maybe different choice of your audio. Sorry, do you want to check? Maybe you have different choice of your audio. Sorry, we still cannot hear you. Oh, yeah, good. Good now. Yeah, we can hear you now.
Oh, okay.
Okay, good.
Okay, sorry about that.
No problem. Yeah.
Good afternoon. Thank you very much for this great opportunity. So my presentation is aimed at addressing the electronic and atomic requirements of abundant photosynthesizers and proton reduction catalysts for artificial photosynthesis. The research presented here aims at addressing one of the most urgent scientific challenges associated with the Earth's rising climate emergency. So to illustrate the global motivation and impact behind this work, we have witnessed over the course of the past decades an increase in the carbon dioxide concentration that is responsible for today's global warming. So this has prompted us to seek alternative clean means of producing, storing, and distributing energy. Given the abundant solar energy potential, one alternative means of producing clean energy is through fuel forming reactions, such as water splitting into hydrogen and oxygen. So the slow kinetics and large activation energy of the water splitting reactions calls for catalysts which, if economically feasible, could see sunlight-driven water splitting as a potential solution to our energy problem. And light energy can be converted into chemical energy through sunlight storing devices such as photoelectrochemical cell. So this is an example of a PEC cell, which consists of two compartments, one for the water oxidation photoanode and the other for the proton reduction. Each compartment contains an electrode, the photoanode and the photocathode. At least one of the electrode is connected to the light absorption component. So it involves a light harvesting unit, and the electrodes are connected externally to allow electron flow. The way to optimize these PEC cells is to optimize each half part of the cell independently. And in my presentation, I will mainly focus on the proton reduction side. I also want to briefly mention that over the course of the past 35 years, we have seen an increase in the efficiency of these photoelectrochemical cells from 1 to only 35%. And recently there were impressive achievements conducted on PNN dope gallium aluminum arsenide that involve scarce metals such as ruthenium and platinum dioxide. And attempts were also made to use less expensive materials and implement cobalt oxides. But although such achievements are important, it is important to remark that such kinds of cells do not provide much room for rational development. So we believe that time-resolved mechanistic insights on molecular systems, whereby each part of the reaction, such as light harvesting, charge separation, and water splitting, can be optimized, can in the long term lead to an optimized PEC cell with solar to hydrogen efficiencies that can exceed the current norm. So the main fundamental research problem that we are trying to address is to couple these light harvesting complexes to catalytic systems. These involve one electron transient states to multi-electron, multi-proton solar fuel catalyst, and being able to do so with cheap, easily repairing and self-processed materials. And in the development of these kinds of systems, there have been two dominant strategies: multi-molecular systems and supramolecular assemblies. In our research work, we have conducted studies on both kinds of systems. In this case, light energy is absorbed at the light harvester and is converted to the catalyst for charge accumulation processes via an electron relay. Alternatively, we have also studied multi-molecular systems, typically in the presence of a sacrificial electron donor or acceptor. So our fundamental work that I will present here aims at addressing the fundamental requirements for the HH and the O bond formation through a multitude of techniques. So we employ in situ X-ray absorption and emission spectroscopy together with ultra-fast time-resolved techniques. We have also applied in situ Raman and EPR to validate the vibrational and the spin density changes. And lastly, quantum chemical calculations are employed to correlate theory to spectroscopic observables. And this comprehensive set of methodologies provides a distinctive correlation between the performances and the stabilities of the catalyst to their structures and the ligand geometries. Through part of this multitude of techniques, we have been able to describe the ultra-fast photophysical processes occurring upon conversion of a range of copper-based photosensitizers in their ground states to their excited states. So time-resolved XANES and EXAFs have both been applied to determine the coordination geometry of a range of copper-based complexes containing multi-dentate ligands. Through time-resolved EXAFs, we have also provided a first hint towards the dissociation or the degradation pathways of some of these heteroleptic complexes containing these bulky diphosphine ligands. And our results allowed us to determine more rational ways on how to improve the stabilities and the lifetime of these complexes for incorporation of more rigid and bulkier ligand supports. We also coupled these photosensitizers, both earth-abundant ones, as well as the typical ruthenium dipyridine photosensitizers with earth-abundant nickel, cobalt, and iron complexes. And by combining ab initio theoretical simulations with a pico to microsecond X-ray absorption techniques, we were able to determine the reaction pathways, but also assign a complete mechanistic pathway followed by these catalysts in the pico to microsecond timescales. Our results allowed us to determine the rate limiting step of this reaction. And this is very important because it determines future ways in which the protonation rate and the catalytic efficiency of these earth-abundant complexes can be further enhanced. More recently, we coupled iridium-based complexes with the typical cobalazyme proton reduction catalyst in a diad fashion. And specifically, we studied iridium complexes with phenyl piperidine ligands, as well as isoquinoline ancillary ligands. And interestingly, the iridium complex with phenyl piperidine ligands showed more photoreduced cobalt-2 upon photoexcitation in comparison to its isoquinoline counterpart. And through combined experiments into the DFT calculations, we were able to find that the reason is because the lowest triplet state for one of the photosensitizer was the MLLCT transition, so the mixed metal to ligand charge transfer transition state, whereas the other one was a combination of CN-centered MLCT and ligand-centered transition, which helps to decrease the efficiency of the MLLCT transition and help it decay back to the ground state faster. I would also like to briefly touch upon our recent work on spin crossover complexes. While it's not related to artificial photosynthesis, we are currently working on a macrocyclic type spin crossover complex that can have an extremely long lifetime. So while impressive developments have been conducted on complexes that go from a singlet to a quintet state, most of them have lifetimes in the order of nano to a few microsecond time scale at room temperature. In this case, we were able to trap a quintet state that had a very long lifetime of around 42.6 microseconds at room temperature. And the extraordinarily long-lived quintet state was due to its macrocyclic nature, which could stabilize a hepta-coordinated, so a 7-coordinated quintet state, and help decrease its reactivity and decay back to the ground state. I will focus the next part of my presentation in presenting unpublishable results that have not been published yet. By combining time-resolved X-ray spectroscopy with TD-DFT calculations, we recently looked at a free cobalt-based catalyst that were purely functional in pure water. So it is important to remark that while impressive progress have been conducted on hydrogen evolution catalyst, most of the studies are conducted in non-aqueous media, where the protons is a source of acids, weak or strong acid. In this case, we looked at free cobalt catalyst with hydroxymethylene, hydroxymethyl, and methylene amine substituents together with the ruthenium photosensitizer, and through time-resolved spectroscopy, we were able to determine a complete mechanistic pathway followed by these catalysts. But importantly, the influence of these amine substituents showed that it is very important to have hydrogen-containing amine groups at the pendant position of these complexes, because they helped in promoting hydrogen evolution and can act as H-H bond-forming relays. So we first start with a steady state comparison of these free catalytic complexes in solution. We find that upon dissolution of the complex with hydroxymethyl group and incubation in water, it adopts the same structure as that with the hydroxymethyl. And upon light excitation through time-resolved spectroscopy, we were able to determine the structural conformation and electronic configuration of the reduced cobalt-2 and cobalt-1 species, as well as explore its protonation events. Similarly, we determined the formation of a cobalt-1 reduced intermediate, which decays back to the ground state within much longer lifetime of the order of microsecond. So I will briefly go through the analysis that my student has carried out. So initially, all the catalysts that we study are always explored in the ground state in order to have an idea of how their experimental behavior compare with theory. So here you have the steady state Zanes and exacts of the free cobalt catalyst in just the solid state. All free catalysts show a rising edge which are different. So for example, if you look at catalyst 1 and 2, it has a 1s2,4p plus shakedown transition along the rising edge. So these shakedown transition corresponds to ligand to metal charge transfer states due to relaxation of the cobalt local electrons in the excited states, and are highly dependent on the metal to ligand covalency as well as the donor character of the ligand. They are typically observed in complexes with fluoridoligands. So catalyst 2 with 2 fluoridoligands exhibit a much more intense 1s2,4p plus shakedown transition in comparison to catalyst 1. On the other hand, catalyst 3, which is the cobalt 2 counterpart, shows 1s2,4pz transition at lower photon energy, which is assigned as the 4p on its pentacoordinated geometry. The pre-edges of all the 3 complexes were also observed at low photon energy, and catalyst 1 with less symmetrical environment, so with which exhibits less centrosymmetry, has a much more intense pre-edge feature in comparison to catalyst 2. And on the other hand, we observed the typical multiplet feature for the cobalt 2 complex, observed at 7709 and 7710 EP. We also measured the exacts of all of these complexes. So as we can see, the cobalt catalyst with the cobalt nitrogen, the fluoridoligands, shows 2 peaks within the first coordination sphere, whereas the one with just 1 fluoridoligand has a weak shoulder at much longer distances. Importantly, our experimental exacts agreed very well with the simulations and the calculated exacts profile from XRD and DFT optimization, showing that our methods and theoretical findings are correct and can be used for determination of the intermediate species along the catalytic cycle. The catalysts were then dissolved and incubated in water prior to time-resolved X-ray spectroscopic analysis. So upon dissolution in water, we see a shift of the pre-edge of all the 3 catalysts, and expectedly catalyst 2 with the 2 fluoridoligands exchange with the aqua ligands shows a much larger shift in the rising edge. This is due to the disappearance of the 1s2,4p plus shakedown contribution, as well as a change of its geometry from a distorted octahedral to a perfectly octahedral state. As well, the charge changes from +1 to +3. Interestingly, the pre-edge feature also changes as the complex becomes more centrosymmetric. So because of this, you have less mixing between the 3D and the 4P states. By contrast, for catalyst 3, we observed that the zanes and the pre-edge are around the same. If, for example, if it were to lose the water molecule completely, we would have seen a more intense pre-edge feature as well as a more intense 1s2,4pz transition. But if it were octahedral, the 1s2,4pz transition would be indistinguishable from the wide line. And the exacts were also measured, which showed a prominent peak within the first coordination sphere corresponding to the average contribution of the cobalt nitrogen and the oxygen distances from the aqua molecules. So this provided us with a first basis of how our catalyst structural conformations are prior to light excitation. So upon light excitation, we have the typical MLCT process from the 4D orbital to the pi star orbital of the ruthenium photosensitizer, followed by intersystem crossing to the formation of a triplet excited state. And this triggers electron transfer from the cobalt-3 to form the photoreduced cobalt-2 intermediate. And this is very important because these types of cobalt complexes are heavily used for hydrogen evolution reactions. We find that one of the catalysts with the hydroxy methyl group is not active unless it's incubated for over 24 hours. So when we dissolve the catalyst at varying times in water, we observe that the transient signal is only pronounced, that we only have electron transfer after around 16 hours. So it is very important that the hydroxy methyl group decoordinates and adopt a hydroxyl methyl substance similar to catalyst 2 in order for it to be active for proton reduction catalysis. As well, here we have the laser off spectra. So just looking at the ground state, we see a gradual isobestic points and change from catalyst 1 to catalyst 2. So a decrease in the 1s2,4p shakedown transition, a shift of the rising edge due to loss of the fluoridoligand, and a decrease in the pre-edge feature as it becomes more centrosymmetric. Upon light excitation, we observed a typical transient signal, which corresponds to the photoreduced cobalt-2. This has a peak energy of around 7722 eV, which corresponds to the cobalt-2 formation, as well as a broad peak in the negative region around 7730 eV, which corresponds to the decay of the cobalt-free species. So this transient signal can be measured at varying times at sector 11 IDD as well as 25 IDD now, which allows us to obtain the photoinduced kinetics and dynamics of the cobalt-2 species. Interestingly, we not only observe changes in the oxidation state of the photoreduced complex, we also observe changes at low photon energies at around 7709 and 771 eV, which corresponds to the typical pre-edge of the cobalt-2 intermediate. All of our experimental results are generally corroborated with TDDFT calculations. So we explored various geometries, a square planar one, a square bipyramidal complex, as well as an octahedral geometry. And the best agreement in terms of difference between these two pre-edges of around 2 eV was obtained for a square planar or a square bipyramidal one. It was therefore essential for us to ascertain their structures for time-resolved examples. And even though the excited state fraction was very low, so in this case, by comparing the zincs of the photoreduced cobalt-2 to a reference cobalt-2 complex that was chemically generated, we found that the excited state fraction was around 4 to 5%, even though this is quite low. We were able to reconstruct the laser-on spectra of the cobalt-2 complex. And indeed, we see two peaks, 1 and 2, which corresponds to the cobalt nitrogen and the much more elongated cobalt oxygen species of around 2.22 angstrom. And this rules out the formation of a square planar geometry and shows that we have a square bipyramidal complex where the water is attached to a metal center as a loose contact. And just by looking at the different bunches from 153 picosecond all the way to a microsecond, we have this data available for free at what was previously 11 IDD. We can monitor the time frame of formation, so the electron transfer to form the cobalt-2 species, as well as its decay back to the ground state. Following the time-resolved measurements for the cobalt-2 formation, we also carried out optical transient absorption. So upon light excitation, we see a very broad band, which typically corresponds to the fluorescence of the excited state of the ruthenium photosensitizer. And this photosensitizer, in the presence of the ascorbate electron donor, forms the reduced ruthenium species, which has a broad absorption band of around 510 nanometer. And in the presence of and the absence of the cobalt catalyst, the kinetics are largely different. So in the presence of the cobalt catalyst, we see that it decays very rapidly. It has an 18-fold enhanced decay back to the ground state, which shows that the predominant quenching pathway in this family of catalysts is the reductive quenching one. And it is important to remark that while optical transient absorption spectroscopy allows us to discriminate between oxidative versus reductive quenching pathways, it doesn't help us map the electronic configuration of the photoreduced catalytic intermediate. For this reason, we carried out time-resolved X-ray absorption spectroscopy in a complete photocatalytic mixture this time of all three catalysts with the ascorbic acid as electron donor. And the ascorbic acid, being a reducing agent, reduces the catalyst right away to cobalt-2. So what you see here is actually the electronic configuration of the cobalt-1 intermediate. And expectedly, catalyst 1 and 2, which adopts the same structure after dissolution in water, has a transient signal at the same energy at around 7716 EV, but that of the three has two different peaks, showing that it has a different, a slightly different structural conformation than the other catalyst. And as well, we were able to monitor the kinetics of the cobalt-1 intermediate, and you will see that the kinetics of the formation and the decay of the cobalt-1 species is the same in complexes 1 and 2. However, it is significantly longer in the one with the methyl group. The methyl group is located slightly further away from the cobalt metal center, whereas the hydroxymethyl group with the hydrogen containing amine can actually promote hydrogen evolution, so it can act as an HH bond relay and facilitate the protonation of the cobalt-1 intermediate. This was interesting because according to the different hydrogen evolution pathways, cobalt-1 is usually protonated to form the cobalt-3 hydride species, which can react either through homolytic or through heteroleptic pathways to evolve hydrogen. So the faster protonation of the cobalt-1 shows that this amine substrate does play a very important role in promoting catalysis. We also were able to corroborate the structure of the photoreduced cobalt-1 intermediate by comparing our experimental spectrum with the TDDFT calculations of various candidates. So we did these calculations, my students and I, through ORCA, and the best agreement for the complexes 1 and 2 was that of a square plane geometry, which has shown to be the typical geometry for CO2 or proton reduction intermediate, whereas that for catalyst 3 was that of a square pyramidal cobalt-1 geometry. And both geometries have been shown to be involved in the CO2 or proton reduction reactions. So in summary, we were able to map a complete mechanistic pathways followed by 3 cobalt complexes that are entirely functional in pure aqueous media and determine the time frame of formation of the various intermediate species as well as their protonation events. More recently, we also invested a lot of efforts on studying an entirely earth-abundant systems. So for the first time, we employed aluminum-based photosensitizers, which upon photoexcitation forms a ligand-centered charge transfer state. We coupled it with an iron catalyst that was functional for both CO2 reduction and a proton reduction.
Just a reminder, you have like 3 or 4 minutes.
Okay. And by combining and by comparing the transient signal with theory, we found that the iron 1 actually adopts, the photoreduced iron 1 adopts a square planar geometry. We also monitored the kinetics for the formation and the decay of the catalytic species. And we are investing currently more efforts on iron-based catalysts that were previously reported in Nature Chemistry. These complexes were known to have nanosecond charge transfer excited state lifetimes. However, our results shows that the lifetime is much weaker and that upon photoexcitation, it forms a quintet rather than a triplet state. More recently, the group of Kelly Gaffney also carried out femtosecond time resolved measurements, and their experiments corroborate ours. And lastly, we're investing a lot of efforts on studying zinc-based photosensitizers and also using them for catalysis, as was previously reported by the group of Oliver Gessner in Germany. And we're also looking at complexes that can be anchored on electrode surfaces, either graphitic surfaces or semiconductor surfaces, such as titanium dioxide and tin oxide. And our future goal aims at encapsulating these light harvesting modules into MOF frameworks that can stabilize the reactivity of some of these catalytic intermediates. So in the future, we have studied a range of earth-abundant photosensitizers, copper, and we are extending our study to aluminum, iron, and zinc. We have further mixed these complexes or coupled them with earth-abundant catalysts for the proton reduction reaction and determine a complete mechanistic pathway followed by these catalysts. And we are working on the anchoring these complexes on semiconductor surfaces to study them for time-resolved approaches. I would like to thank my group members, especially Lucia, who did a large part of the work on the cobalt catalyst, but also Maxime, who is working on the aluminum and the zinc photosensitizer part, and our active collaborators, Jari, Min, and all of our synthetic chemists from all over the world. And thank you so much for your kind attention.
Okay, and thank you for this great talk. So lots of contents and yeah, Nin, you have a question? Nin, you are
yes.
muted. Yeah.
Yes. Yeah, thank you so much for this wonderful talk. I have a question regarding this cobalt catalyst.
Yes.
I was intrigued by your observation of this continuous shift during the time of what, 10 hours, 15 hours?
Yeah.
That's a really long time. So did you observe this continuous changing or actually stop? Because we study a similar complex of cobalt catalyst, and we observed the continuous change, but we thought that the sample was degraded. So even we put in the dark, in the drawer, and no X-ray, no laser, it still change overnight. So did someone do the NMR or some characterization to confirm that is the product?
Yeah, so I did, I measured the steady state characterization of these complexes also at a bending magnet using defocused beam. So there's no radiation damage involved. And we freeze the complex at varying times. So from 2 hours all the way to 16 hours, and we see the same shift. As well, the increase in the transient signal that you see is because there's an incubation time before catalysis takes place. So with a clock electrode, we also measure the hydrogen evolution activity of this catalyst. And there's a very long time, a flat period where we don't see any hydrogen evolution reaction, and suddenly we start to see the catalytic activity happening. So this is not radiation damage, but it's more an incubation period whereby the hydroxy method has to decoordinate from the cobalt catalyst to be active.
Yeah, I do believe you that's not radiation damage. My question was on the, how did you confirm the structure on the right of that equation? Did you use an MMR or some other means to do? Yeah, I'm not asking the radiation damage.
Okay,
I'm asking how do you confirm that because it's not easy to know, why it's continuous changing and what it end up with. So I just curious, how did you confirm that structure?
Yes, our the synthetic chemist, so not my group, but Tony Liobet, who provided me with this complex, did the NMR.
Oh, okay. Thank you.
Yeah. Thank you.
Okay. Oh, thank you, Duxin. So we'll
Thank you
move.
so much.
Okay, thank you. We'll move to our last speaker today. So our last speaker is Trimi Liu. So who is a beamline scientist at our group, the Time Resolve Research Group. So the title of his talk today is Advancing Time Resolved X-ray Absorption Spectroscopy and Post APS Upgrade.
Sorry. So thanks, Xiaoyi. So good morning, everyone. Today why it's automatically. So today I'm so glad to have this opportunity to show you the time-resolved X-ray absorption spectroscopy program at Argonne APS and its development towards the APS-U. So in this talk, at the first, I'm going to briefly introduce why we need the TRXS technique and its success at the APS sector MMID for over 20 years. And now, because of APS-U, this program must be relocated to another new station at the APS 25 IDE. So that means now we are starting a new journey at the new beamline. So here I'm going to update you what we have achieved at the new beamline for the TRXS program towards the APS-U and our future developments towards and after APS-U. So from the previous speakers, you may get the impression on photoreaction for solar energy conversion. And I don't know why it's automatically play. Yeah. So let me check why it's play automatically. No. Okay. I just go this way, maybe much better. Okay. So from the previous speakers' presentation, you may get an impression on photoreaction for solar energy conversion, in which the photogenerative charge carriers usually go through multiple reaction steps across multiple time scales. So look at this picture. It shows a typical Z scheme of photocatalysis. for the water splitting and the carbon dioxide reduction. So you can see at the first, the electron and the hole are photogenerated into photosynthesizers, and they are separated, and then they are captured by two catalysts for doing the redox reactions of the water or carbon dioxide. Actually, as the first step, the excited state dynamics such as charge separation takes place in the time range from sub-nanosecond to microsecond, and then the bond making and breaking happens for generating the new product such as hydrogen, carbon oxide in the time scale from microsecond to millisecond. So during these processes, the electronic and structure changes must be followed across the four-time domain or the reaction coordinates. So the question here is how we can experimentally measure this process and understand the mechanism under this. So let's try again.
So Trumin and Brock said you should unclick the use timing under the slideshow.
Okay, this is
okay, yeah.
Something, yeah.
Okay.
Okay, now it's much better. Okay, so now, at the university labs, people always use the optical spectroscopy to get the electronic and structural information separately. But by contrast, as for the time-around X-ray absorption spectroscopy, which is a development based on laser pump and X-ray probe, it can give us the electronic and structural information simultaneously, because the X-ray is element specific and structure sensitive. So this figure just shows you how the time-around X-ray absorption spectroscopy works. So at the beginning, the sample system is photo-excited from a ground state to excited state. Before it goes to the product state, there are many transient intermediate states. So we can send the X-ray to monitor these transient intermediate states, which are corresponding to a different process in the different time scales. And then we can get the electronic and structure evolution with the time for these transitional states. So as a result, we can understand the whole photoreaction. And so as for the TRX measurements, we can do the TRX time-around length for understanding the electronic structure or excitation state change. Also, we can do the exact measurements for understanding the local geometry structure changing around the atom probed by the X-ray. So as Xiaoyi mentioned yesterday, the time resolution for the time resolution will change from 100 picosecond to 240 picosecond. But I think this will somehow affect we measure the fast process in the time range of picosecond by using the TRX technique. But this will not affect too much on our study the photoreaction, because they usually take place from the a few hundred picosecond to microsecond and even millisecond. Okay, so now I'm going to briefly give you a shorter introduction on the TRXS success at the Secretary MMID. Actually, this program was initialized by Professor Lin Chen, and it has been intensively developed by Dr. Xiaoyi Zhang. So these pictures show you where the station 11 IDD is at the APS, and this picture shows you the beamline layout, at the sector 11. So the TRXAS technique at sector 11 IDD was operated in two timing modes, the 24 bunch mode and the hybrid singlet mode. So let's pay attention to the here. So you can see there are multiple X-ray pulses between two laser pulses. So that means we can have the opportunity to do an efficient laser pump and X-ray multiple data acquisition. Actually, at the sector 11 IDD, this data acquisition method has been developed. So in order to deal with kinds of sample systems from the users at sector 11 IDD, we have developed kinds of easily switched TRXS sample platforms, which can cover the sample systems from a solution such as metal complex and suspension, like nanocrystal colloid solution, and solid thin films, like the perovskite thin films or 2D material layers, monolayer or double layers. So these pictures show you how our sample platforms looks like. Okay, now I'm going to your concrete scientific examples for demonstrating how we apply the TRXS techniques to track the charge flows in the perovskite, in the lead-free perovskite bismuth perovskite nanocrystals. Here is the samples, the nanocrystal samples. So this figure shows how we get the TRXS spectrum. Actually, it's obtained from the difference between the laser on and the laser off X-ray absorption spectrum. Here, I'm not going to the details for how we understand this experimental data, but I just want to say from this difference spectrum, the positive peak here, we can know the photo-generated hole is localized at the Borman side in this nanocrystal, and from this negative peak, we can know the local structure around the Borman side is distorted due to the hole localization. Oh, by the way, here we just did the TRXS measurements by probing the Borman cage. So the further time-dependent spectral and kinetics measurements shows the electronic relaxation represented by the hole localization at the Borman side can be much faster than the structure distortion, can be much faster than the recovery of structure distortion represented by this negative signal, this negative peak. So one thing here I want to point out is as for this 2D TRXS spectrum, it's constructed based on our X-ray multiple probe data operation. So here we just find the electronic and structural relaxations in the perovskite nanocrystal is synchronous, and then we propose. So since we found that the hole is localized the Borman side with the local structure distortion, we propose a small parallel mechanism to interpret our what we have observed. Okay, now on September 26th last year, we got a historical moment. We must say goodbye to our TRXS beam9 at sector 11 IDD, and with the APS-U, this program has been relocated to 25 IDE, a brand new beam9. Everything is brand new, the hatch is empty. So this picture shows you the beam9 layout for our new beam9 running the TRX3 program. So here you can see, since the the new beamline shares the X-ray beam with another beamline at 25 IDD. So so that means we can run the TR-X-ray beamline with a full time. Now it's the new beamline is allocated 75% APS X-ray beam time, and this will be continued after APS-U. So through the hard work of the whole TR group and the support from a spectroscopy group and the BCDA control group, actually we have completely recovered the TR-X's capabilities at this new beamline with the new front-end measure and the monochromators and the new APS motion controls. For the first cycle of this year, we have successfully run 3 user experiments, including 2 international user groups and 1 local user group, and plus 2 staff experiments. As Xiaoyin introduced yesterday, once we got an X-ray beam after APS-U, this new beamline will be restarted immediately. So also I want to say, you have got the information from Emery's talk. The TR-XS-SE program operated by AMO group at Sector 7 IDD will be relocated to 25 IDG also. So the reconstruction is still undergoing. Okay, now I'm going to show you the characteristics of X beam at this new beamline. Actually, this beamline has a really nice double crystal monochromator. It's a brand new monochromator. It's very efficient and stable. So this monochromator also has the multi-layer properties. So this table just show you the energy range we can get from a silicon 111 double crystal monochromator and the multi-layer beam, and with the flux and energy resolution. So right now, as for the sample, as for the X-ray spot size at the sample polarization, we can focus the horizontal down to 800 micro, and but we can make the vertical size much smaller, is 4 micro with a KB measure. Now we are asking another new KB measures. We can, and we hope we can achieve a much better beam profile, the X-ray beam profile at the sample position. Okay, so this table just summarize the laser pump source which are available at the new beamline. So the Ti-sulfur laser in the laser hatch and the dual-active laser from AMO group will be remained at the new beamline all the time. If the user needs other lasers such as Forest and Satsuma, which are portable, they can move from Sector 7 to Sector 25E for users' experiments. So here I just want to say, at this new beamline, we can provide really wide selections on laser pump source, cover different laser photoelectric, laser excitation wavelengths, repetition rate, and the pulse durations. Okay, so as Xiaoyi mentioned yesterday, after APS-U, the hybrid single needle model will be gone. The 24 bunch timing model will change to 48 bunch timing model. But since the current will increase from 100 milliamps to the 200 milliamps, this means the X-ray pulse intensity will not change, and also the laser, the X-ray pulse is becoming denser with a smaller time spacing between two X-ray pulses. Actually, this will benefit our X-ray multiple probe TRXS technique. And we also developed a new faster APD detector, which can resolve the single pulse in the 324 bunch mode. This has enabled us to perform the X-ray multiple probe TRXS measurements in 324 bunch mode. So this figure just shows you a scientific example. We measured the Earth mirror L3 age in 324 bunch model by using the X-ray multiple TRXS technique. So you can see we get a really nice experiment data. So here we also applied the single photon counting in data accuracy method. So I guess after APS-U, this method will be implemented immediately at the new beamline. Also, by combining the X-ray multiple data accuracy technique previously developed at the Sector 11 IDD and the high repetition rate laser pump and X-ray probe cycle method at the 7 IDD from the AM group, we also developed another TRXS technique, which is called asynchronous X-ray multiple probe TRXS. So this figure just shows how the technique works. So actually, this technique is somehow complicated. I will not go to details. So in a word, by detuning the frequency of the laser oscillator, the frequency mismatch can be produced to set up the different time delays between laser pump and X-ray probe in different laser pump and X-ray probe cycles. So in this way, we can customize the time delay steps distribution with a sub X-ray pulse temporal resolution. So here I just show you a scientific example by measuring the iron BPY sample at iron KH with this technique. So you can, we get a really nice data and a Kinetic curve. So when we simultaneously collecting the spectrum at the 6.5 picosecond time space in the early 1.4 nanosecond. So here I just want to point out with this new technique, we have the capability to see unprecedented photoreaction mechanism details with a sub X-ray pulse temporal resolution. So this technique will also be implemented after APS-U. Okay, so you may also know after APS-U, the
Truman, you only have a couple of minutes.
Okay, I will end. This is my last slide. Yeah. Okay, so the APS beam shape will be largely changed along the horizontal direction. So now that means we need to develop new smaller airtight nuclear jet. So we are going to do this during our dark time. So with this smaller airtight nuclear jet, we can take the high repetition rate to laser excitation with our new developed TRXS technique. Also, we can reduce the sample damages. Okay, now I think I can close my talk. So I think at the new beamline, I think the new beamline and the Sector 25 IDE can provide a set of X-ray spectroscopy capabilities to help user measure electronic and structure properties of materials across the multiple temporal and spatial scales. So one thing here I want to say is besides the TRX-ray spectroscopy measurements, 25 IDE beamline also covers the time-round X-ray scatter measurements. such as the TRX XRD introduced by Richard yesterday, and the TR-PDF printed by our beamline scientist Bragg yesterday. So I think here I just want to say our mission is just developing a world-leading time-reliable X-ray spectroscopy and spectral and scattering facility to help users address their high-priority challenges in their researches. Finally, here I would like to thank the whole TR group members and also the M group members and the spectroscopy BCDA group members, our collaborators and users. Now we are warmly welcoming new users and collaborators. So if you are interested in our techniques and want to do some measurements, you can find our contact information through this link. Okay, thank you.
Okay, thank you, Chunmin. This great talk. So any questions for Chunmin? Or we can also start the discussion so we can continue there. So I think now I can stop the recording now. Let me see. Yes.